Hello, and welcome to the first lesson in gases for AP Chemistry. Today we'll be talking about the properties of gases, and we'll look at pressure and different units of pressure, what pressure is, and how to calculate it. And finally, we will wrap up with what I hope is going to be a review of the main gas laws for everybody. The properties of gases differ from liquids and solids mostly in the fact that their particles are spaced very, very far apart. In solids and liquids, the particles are a lot closer together, and they're also not moving quite as fast. So you can see that in gases, these particles have a large distance between them. That and their motion is going to be the root of most of their properties that we're going to look at, and most of those properties we'll come back and look at in a couple of days when we look at kinetic molecular theory, or KMT, which I hope a lot of you will remember from your first year of chemistry. One of the properties that gases have is that they're compressible. With a large space between them, you can push the particles closer together, and so we're able to change the pressures and change the densities of these gases. Gases also rapidly expand when they enter a vacuum or when they enter into another gas, so they fill the container. They also have indefinite volume and shape because of the fact that they fill the container. They will take the shape of their container and they'll take the volume of their container, whatever it might be. Gases are going to form homogeneous mixtures, so they are considered gaseous solutions. Does not depend on their identities. As long as the chemical reaction does not occur between the two gases, the gases should mix, and this is going to end up giving us Dalton's law of partial pressures in a couple of days. This is going to show that the gases behave independently, so let's put that in there as well. They behave independently of one another, as if the other gas particles that were in there did not even exist. Finally, gases are completely described by four quantities: pressure, volume, temperature, and the number of moles of a gas, which we will call N. So gas pressure comes about because the particles in the gas are colliding with the surface of the container they're in. That collision imparts a force from the gas particle onto the container, and within the container, that force occurs over a given area. So pressure then is defined as the force per unit area. Now, if you recall from your physics, force is given by the mass of something times the acceleration of that particle. And so we have the unit of the Newton is our unit of force. Meter squared is the unit of area, and we define the Pascal as 1 Newton per meter squared as the SI unit of pressure. So we're going to be seeing this a lot. We're going to come back again in KMT to determine how this pressure varies as we vary various other functions such as the temperature and the volume and the number of moles of a gas, and to see from a theoretical point of view why they vary. But for right now, we're going to take a look at the gas laws, which we'll get to in a couple of minutes, just from an empirical point of view, which means that we're just going to be measuring things and looking at how the various quantities change. Well, atmospheric pressure is given to us by a column of air which extends from the top of the atmosphere all the way down to sea level. This column of air has a mass, and that mass is attracted to the Earth by the gravitational force of gravity, and that gives it a weight. And this weight of the air, if you remember that weight is a force over a certain area, gives us the pressure of that air. Now, in terms of English units, you may be familiar with PSI, or pounds per square inch, where 14.5 PSI is approximately the atmospheric pressure at sea level, which indicates a pressure of 14.5 pounds in every square inch of area on the Earth's surface. In terms of the SI units, we're going to find that it's going to correspond to a mass of about 10,000 kilograms for every square meter. So that's a huge amount of air pushing down on us. Now, in the early days of science, people did not believe that air had a mass. They didn't believe that the atmosphere actually had a mass. And an Italian scientist named Torricelli invented a device called a barometer. Now, this barometer was a way of measuring atmospheric pressure. The way a barometer works is, if you look at the difference between the left and the right diagram, in the left diagram there's an open tube. So air pressure is free to push down, and across the surface of the liquid, the air pressure is equal all the way across, and so the level of the liquid is flat. Now, one property about liquid is that it will flow in response to differences in pressure. So if instead we introduce a vacuum into the top of this tube, then the vacuum is going to produce no force. Right? There's no air pushing down, there's no particles pushing down, so there's no force pushing down. Yet the force on the outside of the tube, of the outside of the barometer, is still the air pressure. So in order to equalize, in order to make everything turn out to be equal, we have to develop a column of mercury, or whatever liquid we're going to pick, but a column of mercury that has a mass equal to that equal volume of air that it would have displaced. And so in this diameter tube, in any diameter, we'll talk about that in a moment, in any diameter tube we will get a column of mercury which is 760 millimeters tall. And so that became our standard. Now the reason 760 millimeters is our standard is because mercury is very dense. It's over 13 times denser than water. For water, we would need to have a column of water 30 feet high in order to have a water barometer. Now that can be done, but if you think about the lab and the classroom, that's really not a very practical height. This had some practical implications though. In early days of pumps, people were confused as to why vacuum pumps could never pull water up to above a height of about 30 feet. And Torricelli's realization that air pressure is present is what gives it to us. Remember, pressure is a pushing force. There is no such thing as a pulling force. You may have heard in physics that nothing sucks. Even a vacuum doesn't suck. Everything based on vacuum cleaners, based on developing a low pressure area and having the gas in the high pressure area push the dirt into the low pressure area. The height of the column is going to be independent of the diameter. It's also going to be independent of the orientation if you tilt the tube. And I'm going to ask you to go ahead and think about why the diameter of the tube. And the diameter of the tube, of course, is given by the radius. Remember, we have the radius that the area of the bottom, the area of the base is equal to pi r squared. And so the volume is pi r squared h. And so that'll help you to figure out where to go with trying to figure out why the height should be independent of the diameter of the column. All right. The millimeter of mercury is one of the oldest units of pressure. The torr, named after Torricelli, is exactly equal to 1 millimeter of mercury. Now, these are not the units that we're going to see most often. In fact, what we're going to see most often is going to be either the atmosphere, which corresponds to being at sea level when there is exactly one full atmosphere above you. When you go up above sea level, the amount of that atmosphere decreases, and so you say that you're at less than 1 atmosphere. Going back to our units of kilopascals, we have 101.325 kilopascals. Now often we can just round that to 101.3 kilopascals. 760 millimeters of mercury is a unit that you're going to see a lot, and you will see this frequently on the AP test as well. So how do we use these? Well, we use these as conversion factors because there's equalities there. Any one of these units can be used with any of the other units as a conversion factor. For example, if we wanted to determine the pressure, that gives us a height of mercury of 950.0 millimeters, and we wanted that in kilopascals, then we just use the conversion factor That gives us 101.3 kilopascals for every 760 millimeters of mercury. Why don't you go ahead and try that now, and then we'll come back and take a look at the answer. All right, so we set this up. The number of kilopascals, we take the starting number, 950 millimeters of mercury. We put 101 kilopascals over 760 millimeters of mercury as our conversion factor. Let's cross off those millimeters of mercury, which I think I may have done already anyway. There we go. And when you get that, that equals 126.6 kilopascals. Now, does that make sense? Absolutely. 950 millimeters of mercury is about 1.25 if you look at it, just judging. And then 126.6 kilopascals is also 1.25 atmospheres. In a laboratory setting, measuring pressure turns out to involve a device called a manometer. A manometer consists of a bulb to which a tube that is filled with mercury is attached. Now, presumably, this bulb also has somewhere on it, it probably also has some sort of other valve here that you can let gas go in or take gas out. Now, a closed-end manometer works much the way a barometer does, in that up above the mercury here, there's a vacuum, so there's no pressure pushing down up here. All the pressure comes from the height of the mercury, and so that the delta H, that height difference between the top of the mercury and where the bottom of the mercury is here in the gas, is going to give us the pressure of the gas in millimeters of mercury. Another device called an open-end manometer exists, and there's two conditions we have to look at for an open-end manometer. On the left, we can see that the gas is pushing down such that the height of the mercury on the gas side is less than the height of the mercury on the atmospheric side, or the barometer, the barometric pressure over here. Since the pressure of the gas is greater than the pressure of the atmosphere, and you can tell that just by realizing that to push down more, the gas must be pushing by the height amount more than the atmosphere. So we're going to add that delta H to the atmospheric pressure to get the gas pressure. On the other hand, if the atmospheric pressure over here is greater, so here the atmospheric pressure is pushing down more, it's pushing up that amount, so now the pressure of the gas must be lower, and we're going to subtract that delta H from the atmospheric pressure to give us the gas pressure. Now let's take a look at the empirical gas laws. Those gas laws are the laws that we saw back in our first year of chemistry, and as we did back then, we're going to start with Boyle's law. Now, if you remember, Boyle's law tells us that the pressure is inversely proportional. So let's write that out. Inversely proportional. To the volume. So we write that as an inverse proportion, or the pressure is proportional to 1 over V, or let's put a constant in there. Pressure is equal to the constant over volume. If we rearrange that, we get that the pressure times the volume is equal to a constant. If the pressure goes up, the volume has to go down. If the pressure goes down, the volume has to go up, because they always equal to a constant for a given temperature and number of moles of gas. These we're going to hold constant. Since the pressure times the volume is always equal to a constant, if we take our gas at one set of conditions and we change the conditions, then the pressure times the volume at those two sets of conditions must be equal. And now we have the functional formula for Boyle's law that we're going to end up using. So let's take a look. If we take a cylinder whose volume is 1 liter and whose pressure being pushed down and pushing up, remember, if this piston isn't moving, that means the gas pressure up above must be equal to the gas pressure below. The forces are equal, therefore there's no net acceleration. If we increase the pressure in the atmosphere to 2 atmospheres pressure, then that's going to push down on this piston until the pressure inside is equal to the pressure outside. So pressure is always going to equalize, and that's going to push the volume down until the volume is half of that of the original volume. So the pressure went up and the volume went down. Graphically, we can see on the first graph, if we plot, now they've got volume versus pressure here. You can have pressure versus volume. You will get the same result. At high volume, you have a low pressure, and coming down here at low volume, we have a high pressure. Empirically, we want to be able to do something with this line often, with this data, and so what we do is we take the pressure, and this is the reason I plotted it versus pressure. We calculate 1 over the pressure to make it into the inverse, because now we'll find that the volume is equal to that constant times 1 divided by the pressure. And when you do that, that constant becomes a straight line for this now directly proportional relationship. If we look at a particular problem, this is going to come back to now our functional formula for Boyle's law. We're going to start off with a pressure, a volume of 2.50 liters of gas. That's going to be our V1. Our initial pressure is going to be 75.0 kilopascals. Our second volume is going to be 0.50 liters. And why don't you pause the video now and go ahead and do this problem. All right, so now we've done the problem. Let's just set it up. P1V1 equals P2V2. Let's rearrange it so that we're solving for P2. Then we plug in our numbers. Now we have our P1 and V1 in the numerator, our V2 in the denominator. Let's cross off those liters to leave us only kilopascals. And we get 375 kPa as our answer. Notice what happened to the volume and the pressure. The volume went down, so the pressure went up, as we'd expect to happen in this inverse relationship. All right, let's turn our attention now to Charles's law. Charles's law takes volume and temperature, keeping pressure and the number of moles of gas constant, and we'll find now that the volume of a gas is directly proportional to the temperature, or the volume equals K times T, which is going to rearrange to give us that the volume divided by the temperature equals a constant. Now, if we look at our volume and temperature diagram at a given pressure and volume and temperature, now notice we're going to have temperature in units of Kelvin. We'll talk about that in a moment. If we double the temperature, we've got to think about this in terms of the volume changing, the volume changing in response to the temperature, although you can heat a sample up by decreasing its volume as well. If we keep the pressure the same, then what's going to happen is that volume has to double. So the temperature went up and the volume went up, as we would expect to happen in a direct relationship. Now, on the next page, we're going to see that the functional form for Charles's law is at two different conditions that the volume divided by the temperature is going to stay constant, and so V1 over T1 will give us V2 over T2. Now let's see something very important about Charles's law. The volume is directly proportional to T, which means that we can take a plot of a gas at a given pressure and number of moles and extrapolate it back to zero volume. Here's three plots for different pressures, increasing pressure, 0.5 atmospheres, 1 atmosphere, and 2 atmospheres of the same gas, the same number of moles of gas, all extrapolating back to some zero. Now the good thing about this is extrapolating it back to zero gives us not just a linear relationship. If we were to plot versus degrees C, which here would be 0 degrees C, then this would be our y-axis, and it would be a linear relationship because it's not going through zero. It's not a direct relationship. Coming back to what ended up being minus 273.15 degrees C gives us that linear relationship. Well, Lord Kelvin called this temperature absolute zero, and we'll come to find out that there are energetic reasons about this as well, but at a volume of 0 milliliters or 0 liters, that should correspond to a temperature that can't get any lower. If you can't get any lower than 0 volume, which you shouldn't be able to, then you can't get any lower than a specific temperature. And it turned out that that temperature was negative 273.15 degrees C. Now, some of you will remember this 0.15, we don't often include that unless we have 1 or 2 decimal points in our Celsius temperature. Converting back and forth, and I believe you'll find one of these conversions on your information packet. The temperature in Kelvin, notice there's no degrees sign in front of the Kelvin. There's no degrees sign, we only say Kelvin. Is taking the temperature in degrees Celsius and adding 273. Remember that Kelvin is always going to be bigger than degrees C, so you're going to add to get to Kelvin. You're going to subtract 273.15 to get from Kelvin to degrees C. All right, now this gives us a very important point, is that every one of these gas law problems is going to require us to convert any Celsius temperatures into Kelvin. So the size of each unit is equal. So if you put two thermometers up next to each other, one in the Kelvin scale, one in the degrees C scale, you'll find that they line up 1 to 1 in terms of the size of the unit. It'll only be off by 273.15. All right, so let's do a problem involving Charles's law. Hopefully this is going to be fairly straightforward to you. We're going to start off at a particular volume. Volume 1 and a particular temperature 1. Now remember, this is in degrees C, and we're going to heat this up to a second temperature. So think about what you've got to do. Pause the video, go ahead and set things up, and then come on back. Okay, so you're back. So here is the first thing you always have to do: set up the conversion of the temperatures into Kelvin. And then we can go ahead and set up our equation. We know that V1 over T1 equals V2 over T2. Rearrange this to solve for V2. Plug in the numbers. Cross off the Kelvin that cancel. And we're going to be left with 1120 milliliters. Notice we don't have to change the milliliters into liters because it's going to just come through on the end. If you wanted to change it into liters, you could, as long as you do that properly. That won't be incorrect. The temperature went up, and at the same time the volume went up, and so our direct relationship holds. Now let's take a look at Gay-Lussac's law. Gay-Lussac looked at pressure as a function of temperature, and we found that we had that same direct relationship, that for pressure of a gas is proportional to the absolute temperature. We have to say absolute temperature now since we know about absolute temperatures. So again, the same things. Pressure is equal to a constant times T. Pressure divided by T is equal to a constant. And as before, we'll rearrange that and have our two separate conditions so that P1 over T1 is equal to P2 over T2. Very simple problem to do for that. So here we have a volume. Is that important? Remember, we're only varying P and T where the volume and the constant are volume and the number of moles are constant. Often this will say a rigid container. That will give you a hint that we are not changing the volume. So here's our first pressure in atmospheres. Here's our first temperature, and here's our second temperature. Don't forget what to do. Go ahead and pause the video and run the calculation. We'll see you in a moment. All right, so first thing you did is convert the temperatures into Kelvin. Then let's set up the problem, rearrange to solve for P2. You could also have given the second pressure and been asked to find the second temperature. Set it up, cross off the Kelvin, and let's do the math. And we find that we have new pressure of 7.38 atmospheres. Again, notice the pressure went up when the temperature went up, and so our direct relationship holds. Now, these are the three main individual gas laws. Each of them we got to by holding two of the four variables constant. That's not always going to be the case, and so what we can do is we can combine all three of the gas laws together to give us the combined gas law, which looks exactly like this. Now this formula is going to be what you find in your information packet. So often you'll see that I'll do something like this, where if we have an information pack formula, I will put it in a box to remind us. Make sure you know where that is on the information pack so you don't have to go searching through it. In this case, only the number of moles of the gas is going to be held constant. As I said, this is the equation given in the exam information packet. Now, since this is the only information given, how can you get back out to the other three laws? Well, the great thing about this is that if you want to get to one of the other laws, or to one of the previous laws, what you're going to do is cover the quantity that you want to hold constant. So for instance, in Boyle's law, we also want to hold T constant. So let's cover up T, and if you cover up T, then you'll see that you've got, as Boyle's law gives us, P1 times V1 equals P2 times V2. You can do the same thing for the other two gas laws. So if we want to do Charles's law, where in Charles's law now we're holding P is constant, let's cover up P, cover up P2, and notice we now have V1 over T1 equals V2 over T2. Finally, for Gay-Lussac's law, we're only going to hold the volume constant. So let's cross off volume 1 and volume 2, and as you can see, we have P1 over T1 equals P2 over T2, and there is Gay-Lussac's law. In this law, in the combined gas law, you cannot see the relationships as easily as in the other two gas laws. So when we do problems with this, it's not going to be as straightforward whether you'll be able to reasonably look at your answer and know whether or not you've got the right magnitude. All right, finally, in the very end, we're going to talk about a gentleman that you may have heard of named Avogadro. Avogadro's law tells us that the volume of a gas maintained at constant temperature and pressure is directly proportional to the number of moles of the gas. Now, some of you may remember a little song about equal volumes of gases at the same temperature and pressure have the same number of molecules. But what does this mean? That the volume of a gas is proportional to the number of moles of a molecule of gas, and so volume is proportional to N, V equals K times N, keeping pressure and temperature constant. Now, we don't usually set this up in the proportions like we've been setting up Charles's law and Gay-Lussac's law. Instead, what we do is we hold pressure and temperature to a very special set of constants in which the pressure is 1 atmosphere and the temperature is 0 degrees C, and we call that standard temperature and pressure. You may remember that. Standard temp and pressure. And at these conditions, the molar volume of a gas is given by 22.4 liters for every mole for an ideal gas. And this is generally what we're going to do. We're going to use this as a conversion factor especially when we get to things like stoichiometry of gases in a bit. And these conversion factors are going to allow us to determine the number of moles. Also, one of the things we're going to realize, and this is going to be in one of your homework assignments, is that when we have the volume being proportional to the number of moles, that means that at constant pressure and temperature, that the coefficients in that balanced chemical reaction, coefficients, can show either a mole ratio or a volume ratio because moles and volume are directly proportional to each other. Let's just take a look at one quick problem that we can do using our conversion factor. Suppose we want to know the volume of 35.0 grams of oxygen gas at standard temperature and pressure. So go ahead and use your dimensional analysis, stop the video, and come back in a moment and let's see how you did. Alright, so you're back. The first thing you should of course realize is that if you want to get the volume of oxygen and you're starting in grams, first thing you need to do is convert to moles. So let's convert to moles. You didn't forget that there's two oxygen atoms in every molecule, right? Grams of oxygen, cancel out. Now for moles of oxygen, let's employ our conversion factor. We have 22.4 liters of oxygen for every mole of oxygen. Again, we'll cross off the moles of oxygen. And finally, our answer, 24.5 liters of oxygen. Does that make sense? Sure. 35 grams of oxygen is a little bit over a mole. So 24.5 liters is a little over a mole in terms of volume. All right. So the homework on this lesson is on your syllabus, and it's going to be due on Monday because we have our Chapter 4 test on Friday. All right, so if you want to look over anything again, go back and look at the video, replay it. Hopefully everything makes sense, and we will see you tomorrow.